Hi everyone, today we're talking about graph transformers on directed graphs, and this is a paper by Geisler, and he'll go into it with us.
So I'm happy to be here. I'm going to present our ICML paper on transformers meet directed graphs. So we are going to deal with more or less a vanilla transformer most of the time, which you see illustrated to the left. And the question is like, how can we feed in directed graphs, like some examples we see to the right. So we have some nodes connected in some arbitrary way with some directionality, and additionally we might have node features and so on. Can you see my mouse still?
Yep.
Okay, perfect. This brings us to the main question. Is there some region to the right which you can't see in the sharing? No, this should work, right?
Yeah, as far as I can tell, we see
Sometimes if you have like those video overlays, then there's some area that's not properly displayed. Okay. So again, to the question. So how to generalize transformers to directed graphs? I guess transformers, most of you should be familiar with. Those are working on sequences. And sequences we can think of as directed graphs. So just like in a linear connection. And there have been also graph transformers proposed previously that more or less most of the time work with undirected graphs. However, sequences and undirected graphs are actually two disjoint sets, and in this work we try to overcome this and to propose proper generalizations that would work for sequence tasks and would work for graph tasks as well, where we then obviously also want to exploit the directionality. For this, as I already hinted, we're going to have two direction-aware positional encodings. One is motivated from a spectral graph theory based on a direction-aware generalization of the Laplacian called the Magnetic Laplacian. This is where I'm going to talk about most of the time. So probably like 40% or 50% of the talk, I'm going to talk about this first direction. And I'm also going to give some insights on how to come up with those directional random walks. Before I dive into that, I also want to motivate like why directed graphs are important in the first place. So I guess there are multiple reasons. Obviously, if I ignore direction, then I will sacrifice expressivity. So for example, in a sequence, if I ignore the direction, then I cannot distinguish what is the first and what is the last token. And obviously that can yield to some expressivity issues in the end. And if we model some input domains with directed graphs, that's the second advantage. Then we can also model some symmetries and maybe get some advantage, especially over the sequence representations that is very dominant in the beginning. So I'm especially focusing on the green boxes, so the position encodings and how to leverage symmetries with some example input modality. And for the expressivity, I mostly refer to the code, so I will only scratch that on the surface. So our first motivation, or the application, and actually also our motivation of looking into this direction was originated in the question of how do we actually represent code. So for code, here's some simple function. I guess I don't have to explain too much about this. So this is just like some F1 score calculation. And then the question is like, how does a transformer, how does a language model actually encode this? And for this, we tokenize the source code. So we go from left to right and line by line, and then we end up with some token representation. What we propose to do instead, to gain some advantages here, is to use a directed graph to model that modality. So for this, we first construct an abstract syntax tree that gives us some hierarchy, and then we do some dependency analysis between the different elements in this tree, and then we end up with some directed graph. This directed graph, of course, like for such a simple function, is just like a DAG, so we don't have any cycles, but we can handle with this construction any arbitrary code. So also like loops and exceptions and all those things that then in the end will introduce loops into such a structure. And what is the advantage of doing that? One of the things one could achieve with that, or what we achieve with this, is that we get invariant with respect to certain reorderings of statements. So for example, let's have a look at a recall statement. if I move the recall statement 2 lines up, that's still like semantically the very same function, right? Nothing really has changed. All that the recall calculation depends on has been calculated at that point in time. So there's no difference. And there are also some commutative operations like the multiplication and addition on the bottom. And if I swap the order of recall and precision, this will also yield the very same code. Of course, if you think about the sequentialization, the tokenization, which I discussed before, this will yield in 2 different sequences, right? So that's something that the transformer then has to deal with, or whatever model we actually want to apply here. And with this graph construction, we map like all those possibilities to a single graph. And to me, at least, it's surprising that for this simple function, just considering those 2 invariants, we already find 4,096 possibilities of rewriting this F1 score, and therefore this certainly has like some advantages. Okay, so this was a little bit the motivation. So now talk a little bit about like how does a transformer actually understand input modalities, and then from that we can derive on how does this generalize, or how can we generalize this to directed graphs, right? For this, I should note that the transformer per se is a permutation equivariant. So if we permute the inputs, the outputs will be permuted in the very same way. And to make this transformer then like aware of the order of the structure of my input domain, I need something like positional encoding. So I'm adding this to the node embeddings, and by this I then have like this structural information or this description of my input domain. For sequences, one of the common ways proposed in attention is all you need are sinusoidal position encodings. So here illustrated as a bitmap, and each of the rows, so we have I think sinus and cosinus waves. So on the top there are the sinus waves, on the bottom there are cosinus waves, and we have like a couple of them of different frequency where we encode then the node integer position. So in orange we see some low frequency, and in blue some higher frequency. And then we can take one of those columns as positional encodings and add this to the node embedding. So here for the sequence, so I just like have the very same sequence as before. It's just now rolled up to save some space. So this is just like some directed graph where I have the tokens, and those are sequentially connected. And if I calculate those sinusoidal position encodings, so here for this blue and orange, then I might end up with something like that. So the first node with those sinus waves only will of course have a zero embedding, and then there are like 2 sinus waves of different frequency where I'm just like taking those for the node positions. People have realized before that those sinusoidal position codings, like combining a lot of different sinus and cosinus waves, is actually quite similar than the discrete Fourier transformation. So here again, this directed graph, the nodes ordered, that this works with the illustrations and so on here, but this is not a necessity for the general principles. And then those sinusoidal position codings correspond like to the discrete Fourier transformation. To give you, question?
Because you say the nodes are ordered, but this is not necessary for the underlying principle here. But sort of for the sinusoidal positional encodings, right? We need some starting point that they're not translation invariant, so to say. You can't you can't shift your sequence, and you still end up with the same positional encoding.
Yeah, I should probably clarify. So of course I need to know the node position, and then I have some equations to calculate those sinusoidal position encodings. Afterwards, I can permute those, right? Once I have the encodings, but of course, for the encodings to obtain them, I need this order, right? So kind of like to encode the first node and the sinusoidal position encodings, I'm then plugging in the node index position. And for this, I need to know what is the first node, what is the second node, and so on and so forth, right? That's all I meant. I mean, like, especially later, if we go like into graphs, then this is not necessarily like true anymore. Then we can have arbitrary permutations. But like for most of the time in this talk, I will have like nicely ordered graphs just to make the visualization flow. Yeah. That's basically all I wanted to say. Yeah. So back to the position encodings here. Described a little bit more in detail. So we have like sinus and cosinus waves, we have the node integer position, and we multiply this by some frequency. Here for the sinusoidal positional encodings, I've written this out. For the discrete Fourier transformation, I just like denoted this with fj. So they're like different frequencies, and we have sinus and cosinus waves here. So that's basically the relationship. Of course, the frequencies are a little bit different, some minor things, but that's kind of like why people say like those are very, very similar to each other. And I agree to that extent here. Going one step further, now we're talking about graphs where we also want to represent like more complex graph topologies. Then we can generalize this, or this is at least related or very similar. It's not a proper generalization. We can use the so-called graph Fourier transformation. So we use the eigenvectors of the Laplacian, and that also yields some basis function. So to the right, we see the eigenvectors of the Laplacian for this unordered sequence. And we see also in the bottom, we have higher frequencies, and on the top, we have lower frequencies, and those are somewhat related. Of course, there's a reason that I plotted the undirected sequence on the right, and the reason is rather simple. This is a basic assumption that kind of makes this graph Fourier transformation work in the first place. So to understand us a little bit like how this works and how this corresponds to each other, I will give like a very brief introduction into like the relationship to discrete to signal processing via the discrete Fourier transformation. I guess like, yeah, if you're familiar with that, that should be easy to follow. If not, then I guess you should be still able to grasp the gist, but maybe some details will be a little bit opaque here. Okay, so in this in signal processing, what we commonly do is we have some input signal, and then we want to convolve this with some filter, and then obtain like some transformed output signal. That's basically also very similar to what we do in machine learning. And one way to do this in signal processing, or a classical way, is to use, for example, the discrete Fourier transformation, and then do the inverse discrete Fourier transformation. So those operations cancel each other out, and therefore this is perfectly the same. However, the main advantage is if I do discrete Fourier transformation of the filter and of the signal independently, then this convolution becomes a multiplication, which makes things much easier. And I can also write this in matrix form over here. So we have the input features, we do some matrix multiplication times input features to go into the spectral domain. Then we multiply with a diagonal matrix, which corresponds to this element-wise multiplication. And then we do the backward transformation to the spatial domain. And for convolutions on graphs, we can write something that looks very similar, just like by something called the graph Fourier transformation. We also have some filter, we also have some signal. Those are now node embeddings, and we can define some convolution. We can define a graph Fourier transformation just like by writing it in this very similar way. But here we have like this matrix V popping up, which is not the Fourier basis anymore, as we have it with the discrete Fourier transformation. Now we have this V matrix, which is an eigenvector, or is the matrix of the eigenvectors of this graph Laplacian. So we decompose the graph Laplacian using this eigendecomposition, and then we obtain something very, very, very similar here. This is then those eigenvectors are then also called like the graph Fourier basis, where we assume that the eigenvalues are ordered. It's something I'm going to assume for the remainder of the talk. Typically, it's not really important, just like to ease the notation. So we order the eigenvalues, and then correspondingly, we obtain this matrix of eigenvectors, and we take the k lowest of those typically in a transformer. So this has two main advantages, I guess. The first is this is independent of the number of nodes. And the second is even for larger graphs, like computing this partial spectrum of the graph is still tractable, as the complexity is like km with the number of edges m over here. So this is something we can compute even on rather large graphs somewhat efficiently.
What happens if we have a graph with only 5 nodes and k is 10?
Sure, like that. The typical way is then just to do padding, right? And that's something that also works here. It depends a little bit on your architecture and how you then like handle the padding internally. But in the end, that's what's happening in the implementation.
Yeah. Can you go a slide back and I'll
Sure.
say some words and you say how wrong I am. So we have our X here, which are like features on a graph now, right? So it's a vector of some values, and each value is associated to a node. And now we take this our graph Laplacian, right? So by taking our adjacency matrix and fiddling around with our adjacency matrix a little bit, subtract it from the degree matrix, and then we take the we take the SVD of this graph Laplacian, or we do our eigenvalue decomposition, and then we have our eigenvalues and our eigenvectors. And now we take the transpose of the eigenvectors and we multiply with our features. So that means we kind of project our features onto these eigenvectors. And then we're in this Fourier space. And that's what you call doing the graph Fourier transform. And then we multiply with whatever we wanted. We just do the same Fourier transform as well with our with what we wanted to multiply with to end up with this G hat thingy. Is that right? How do we go from to G hat?
This G hat is typically something fixed. Here it's written as a function of the spectrum, and then you do this element-wise multiplication, basically, right? This is a diagonal matrix, and then we do this.
But what you say, like we want to do a convolution, so we want to convolve G with our X, right? And now I have my G and I have my X, but I know how to get my graph Fourier transform. We just said how to do it, but now how do I get my G hat if I only know my G?
I mean, in principle, like if you specify G in the spatial domain, which we typically don't do in the graph world, then you also need to do the very same multiplication. Then it's also V transpose times something in the spatial domain. Typically, that's not how we parameterize it, so that would be very uncommon to do. You rather would parameterize like G hat directly. To also like save the step, and I don't know. That's also like what you would do, like if you now think about like a graph neural network, like how you end up from this to a graph neural network. Then basically this, what you're doing in the spatial domain specifies what this G actually is, right?
Yep. Okay. Very nice. Then let's continue.
Okay, thank you for the question. Okay, I think I was done with this. So we take the k-lowest eigenvectors typically for like to be independent of n and for computational reasons. But yeah, we have seen that kind of for this graph Fourier transformation, we have this eigendecomposition. And this eigendecomposition is exactly the thing which makes it tricky for generalizing this to directed graphs. Because for the eigendecomposition to be well behaved, for example, that the eigenvectors that it yields are orthogonal and so on, I need some properties of the input matrix. One of the common properties is like that it's real and symmetric, which works if I have an undirected graph. If I have an undirected graph, then A will be a symmetric matrix, D is just a diagonal matrix, and then L will also be symmetric, and therefore the eigendecomposition is well defined. However, if I don't make sure that I have a real symmetric matrix and do the eigendecomposition, I might end up with some eigenvectors that are certainly not really useful positional encodings. If I look to the left into this bitmap illustrating the eigenvectors. So what are the ways? How can we overcome that? First, I want to note that like for certain directed graphs, you don't need to do anything, regardless of the asymmetry in L. One of those matrices are circulant matrices, which occur, for example, like for a ring as we have over here. I guess like this is also quite well known. If you do then the eigendecomposition of such a matrix, of this matrix L, then you will also end up with eigenvectors that correspond to the Fourier basis. So what we've seen earlier with the discrete Fourier transformation, for this kind of matrix, we will obtain exactly those this Fourier basis as the eigenvectors. However, there's some difficulty to directly generalize those discrete Fourier transformation to arbitrary directed graphs, and this is, as you see here, this assumes that there is periodicity in your signal. So your signal is periodic; it repeats all over the time. So how do you actually define what is your first node? In the discrete Fourier transformation, I have the main advantage that I know what is my first input in the sequence. In a general directed graph, I will have lesser control about like determining what is the very first node or something like that. Another, I guess, natural way of doing this is to do a singular value decomposition. This has been proposed before. So for example, we can do the singular value decomposition of A. This yields perfectly valid results. So we get real matrices or singular vectors and singular values out of this. But I want to convince you that this might not have like the perfect properties we want to think about, like if we think about like positional encodings. And of course, it's somewhat hard to interpret the singular vectors in the end. So for example, again, our directed sequence, I now took the adjacency for 5 nodes. I just threw it through NumPy and made a low rank approximation. So we're still, we're again like considering like a subset of the spectrum, and then I ended up with those singular vectors and singular values. I reconstructed A to understand what is contained in those singular vectors, and as you can see, 2 of the entries are basically cancelled out with this procedure. So there might be some issues if you want to use this as a positional encoding. At least for sequences, this will most certainly not work very well. Okay, so what are we proposing to do is to use a direction-aware Laplacian. Specifically, we propose to use the so-called magnetic Laplacian. The magnetic Laplacian is motivated by physics to describe some magnetic flux. It also appears in quantum physics and so on. It has been applied to machine learning before. So for example, there's a spectral GNN using the magnetic Laplacian. This has been used for community detection and so on. And we can also use this to make or to come up with positional encodings that generalize to directed graphs. So what do we do here? So it's basically just an extension of the graph Laplacian, which we've seen before. So we have the degree matrix minus the adjacency matrix. One specialty here is that those two are for the symmetrized graph. So here we symmetrize on purpose, and then we multiply this element-wise multiplication with an element-wise exponential of this I theta. And this I theta is then the thing that encodes the direction. So this is defined for the difference between node u and v it's defined to be 2 pi q and then auv minus av. So depending on the edge direction, this will either be +1 or -1, or some weight if we have a weighted adjacency matrix, or it will be 0 if like both are the same, which means there's no edge or there is an undirected edge. So we handle also this case quite nicely here. And we have this exponential with some complex number now. So you might wonder, if this is not symmetric, what have we actually gained by doing this? We're again having like something asymmetric. The main point of this construction is that this matrix has some special properties, and it is a Hermitian matrix, which means if I take the conjugate transpose, I end up with the very same thing again. And as you might recall from your linear algebra class and so on, for Hermitian matrices, the eigendecomposition again is well behaved. So for Hermitian matrices, the eigenvectors are again orthogonal, the eigenvalues are real, which is probably not too critical, but they are. And yeah, we can use those then as positional encodings, as I'm going to convince you soon. There's one hyperparameter, which is the potential, which I will discuss later as well. So before I go into some examples of the eigenvectors, let us have a look at what does this magnetic Laplacian actually look like. So here we again have the definition of the magnetic Laplacian. This time just like the theta, directly like expanded. So it's A minus A transpose. And yeah, we can then look at two example graphs. So again, at a directed sequence and at the undirected sequence. For the directed sequence, if I choose Q to be 1/4, then this will resolve to like a purely imaginary modeling of the direction. So depending on the edge direction, I will have a minus I above the main diagonal here and the I below. The main diagonal of this matrix remains the same as we had it for the graph Laplacian. If I would have undirected graph, then of course A minus A transpose is the zero matrix, because it's same for every entry. And yeah, I will end up with the graph Laplacian, the very same thing as we had before. So this can also be stated a little bit more general. So for undirected graphs, we obtain the graph Laplacian if we do some appropriate normalization, right? So there was this normalization where certainly different choices. I'm not sure if there's like the single best choice, but yeah, if we do that, we ended up with this. Okay.
Can you lose a few words on the matrix exponential?
It's not the matrix exponential, it's element-wise exponential. I hope I said that, I think. Or did I miss that?
No, you probably said that, and I didn't pay attention.
It's some definition with some minor tweaks. So it's an element-wise exponential, and therefore this is just like Euler's equation, as you know, like cosine is the real part, minus I plus I minus sine is the
That's very nice. Yeah, that makes everything much simpler. Yes, thank you.
yeah. Having the matrix exponential here would make it correct. I guess you can look up Euler's formula. I think I didn't explain it correctly. So we have the sinus of the exponent, and then Anyways, So I was here, and then we end up with this thing. So if theta is just like zeros, then exponential, like the exponential of zero element-wise is just like a matrix of ones. This is multiplied then by the adjacency, and therefore we end up with just the adjacency. And for an undirected graph, AS is equal A, D is equal DS, and therefore this is the very same. I hope this makes the explanation complete. Okay, anyways, for other directed graphs, at least for some, there's also some special relationship. So for example, if I have trees or sequences, then the eigenvectors of the magnetic Laplacian are a function of the eigenvectors of the graph Laplacian. Function, take it with a grain of salt, like eigenvectors are not unique, but if I know the eigenvectors of the graph Laplacian, then I can obtain the eigenvectors of the magnetic Laplacian by a very simple construction. Here I'm illustrated for a sequence. So we do this eigendecomposition. Now I subscript the eigenvectors with Q here to make this distinction. And then the eigenvectors of the magnetic Laplacian equal to this S matrix times this VU times the eigenvectors of the graph Laplacian. And S is constructed to be a diagonal matrix with e to the power of I 2 pi qv, where v again is the node integer position. So this is 0, 1, 2, 3, as we had it for sinusoidal positional encodings again. Of course, I don't have to do this manually later. This is what this will resolve to if I do the eigendecomposition. So here the order doesn't really matter anymore, as long as I have like this graph structure. And yeah, we also see this encoded here in the node color. So black means there's no imaginary component, and blue means like there's it's very imaginary the results, and this is the first eigenvector, which is I will talk about this in a second again. Actually I'm already on this slide. Of course, I've been talking now a lot about sequences, but actually we're not really too much interested, at least in sequences. The main point was we want to obtain something that's actually general. So here we have 3 different graphs just to illustrate this a little bit. For the sequence, the first one is what we've already seen. Here I have to say the size of those nodes encodes the magnitude and the color, the phase. I've normalized away the absolute, like the value ranges just like to give like some qualitative insight, but I guess that should suffice. So for the sequence, for example, as I've illustrated before, we have this S matrix, and therefore the phase shift is also node dependent and not dependent on the eigenvector. So for you see that for all the eigenvectors, here are the first 4 eigenvectors. This is from the lowest eigenvalue, then from the second lowest, and so on and so forth. The imaginary part for those simple graphs is the same over all the eigenvectors, and the fluctuations are only due to like whatever we would have done anyways with the graph Laplacian. But importantly, we can also handle more complex graph structures. For example, if we have a cycle over here, then this changes how this imaginary part and so on looks like. Also the magnitude in this we don't have like a constant eigenvector anymore, as we had with the graph Laplacian. There the first eigenvector is constant. If you're familiar with those eigenvectors, some of those things don't hold anymore if we have cycles, but we can represent the position. And if you look at those eigenvectors, I guess you will find some patterns on how this in the end turns out, and how this node position is encoded in here. Of course, this also works for trees, and we give like a couple more examples in the paper, just like to convince you that whatever this is yielding, that those eigenvectors are somewhat useful to predict the node's position and the relative distances. After all, that's what positional encodings should do, in my opinion. One thing I have neglected here and also in the slide before is that to do this, there is some normalization going on. So eigenvectors, or canonicalization, if you want so. Eigenvectors are not unique, and therefore we need to deal with this ambiguity. I think there was also a talk a couple months back about sign and basis invariant neural networks that basically addressed some of the aspects here, mostly focusing on real eigenvectors. One thing which I also didn't say explicitly, the eigenvectors we are now obtaining are complex, which I would argue is not a big deal, because, like, I don't know, for sinusoidal position encodings, that's probably what we've done all the time. I see some messages in the chat. Is that something I should answer?
Yeah. I mean, yeah, let's go to the previous slide. Is the phase ranging from 0 to 180 or 0 to 90 when coloring the nodes?
It depends. Like what I haven't discussed, what I'm going to discuss in a couple slides is that there was this potential Q, and this potential Q in the end determines how much the phase shift will be. So depending on how your hyperparameter choices are, yeah, the phase shift might be very small, or it might be like even multiple rotations, right? If you choose a very large, it's basically a rotation in the end what we are looking at if you talk about phase, right? And we can even like make multiple rounds and so on. So there's something you should consider, but I will talk about this in a second. Here, everything is normalized away to make the gist or the essence of this thing stand out.
Yeah.
Symmetrization. Yeah, like 0.5 A plus A transpose, I guess is a totally valid symmetrization. I'm just saying, like, it's not the only way you could symmetrize, because this way the directed edges would always have like half of the undirected edges as a weight, right? Because if you do A plus A transpose and you actually have a bidirectional edge, then you will end up with the value 2, you divide it by 2 and you will have value 1. And if there is no bidirectional edges, this is just like true, like 1 in one direction, then you will end up with 1/2 as an edge weight. So there might be like applications where you want to use different normalizations, but I guess this is totally fine to do. All possible directed graphs of specific order map to the same graph. The information, I'm not too sure what you mean by that, Muhammad. So what, like, I don't know if it has already cleared in the meantime, also this question. So the part up here, you're absolutely right. This is not aware of any direction, but we have this exponentiation. And here A minus A transpose is without the symmetry without symmetrizing, and therefore this contains directionality. Yeah, exactly. Okay, I think those were.
Yeah,
there was a question by Matteo, which I guess I addressed. Should I jump back or should we continue?
Yeah, no, I think you talked about that sufficiently. Like this was back when we were talking about why the Laplacian is not always clear.
Okay, then yeah. Then let's jump back. Okay, I don't see the chat anymore, but I think
don't worry, I'm on.
Okay, perfect. I was just seeing that there's a 4 standing, so I was wondering. The last time I looked, it was a 1. Okay. Anyways, so back to the ambiguity of eigenvectors. So here we have this equation, right? This describes this eigenvector in the first place. So we have this matrix here, the magnetic Laplacian. We have some eigenvector, the ith eigenvector, which corresponds then to the eigenvalue times this eigenvector. And you will probably agree that this is equivalent to the way how I write it to the right. So here I just multiply this eigenvector with some constant ci, which is a complex number except 0. And for this, like this equality obviously also holds. I've already rearranged it just like to make the main point that this is scaling the eigenvector or rotating the eigenvector here. Of course, we have the very same thing for real eigenvalues. This is nothing specific to complex eigenvectors. The main difference is for eigenvectors, nobody would get the idea to choose some complex factor here. You would just choose some real factor, and then this corresponds basically to the numbers on the real line. And if we do look at the next point, this will then correspond basically to the sign ambiguity, because we typically will choose the eigenvectors v of a certain magnitude to be of magnitude 1. And equivalently, we can also say that the matrix of eigenvectors, that this is a unitary or orthogonal matrix in the real case. And so if you take the matrix times the eigenvectors times the eigenvectors conjugate transpose, we will end up with the identity. And with this, the magnitude is gone of this ci. So we have like the magnitude fixed of the vector, and then for real eigenvectors, this will just mean that c might be -1 or +1, which is exactly the sign ambiguity. Additionally to that, we still need to choose like some rotations. So we've chosen the magnitude. Here we do a very similar approach than how this is dealt with, like in sinusoidal positional encodings and in the discrete Fourier transformation and so on. We choose some node to be like the first node. This is one choice we did. There are certainly other choices. But yeah, what are we doing specifically? So in our applications, we realize that we always have a source node. So we take the foremost source node, which is a node in degree 0, to choose this to be our origin. So this is something we then normalize to be a real positive real number, and therefore we can choose this ci in a canonical way. But I guess there are multiple ways how you could choose the rotation here. This is just like one of those examples. And of course, if you're actually dealing with like arbitrary directed graphs where you maybe have circular structures, then of course you need to come up with something more refined, and then canonicalization might not be sufficient for your application. So let us make an example here for a sequence. Or I forgot to write down this is for a sequence. So for a sequence, we have this relationship. There we have this S matrix describing the node position. And here, since like everything was assumed to be ordered, we can just like choose this CV constant to be equal to 1. And then for the very first node, this will be something real. And we obtain this positional encoding. Another thing of ambiguity, or another source of ambiguity, are repeated eigenvalues. We looked into our applications, and for them it was of minor importance. So those are an indicator of a lot of symmetries in your problem, and they didn't really occur for us. But yeah, they might also might appear in your applications. So that's something you should spot and you should be aware of. So check this if you want to apply such encodings. If you actually have repeated eigenvalues here. Okay. Another thing, which is also also a little bit arbitrary at the moment, is this potential Q, which then determines like how big is this phase shift. And there's actually a very nice analogy like to sinusoidal positional encodings. So here we have again the eigendecomposition for a sequence. We have again this S matrix where we encode the node position V, and for the very last node we obtain like this total phase shift to be like 2 pi q times n minus 1. So this is like the total rotation we're going to apply. And this is basically what we had earlier. So we have again a node position and we multiply it by some frequency 2 pi q. And this is the very same as we had it in position encodings, right? There we have some node positions and we multiply it by some frequency. Here in the case of the magnetic Laplacian, we just have a single frequency, like in terms of q at least. We can just choose one, and therefore q therefore plays a similar role than the largest frequency we have in the sinusoidal position encodings. So up to like adding this 2 pi factor, we then therefore have like a very similar relationship to this 1 over 2 pi 10,000 as we have it in the sinusoidal position encodings. Okay, so now I've been talking a lot about like those eigenvectors. Now a little bit like how do we actually use this in our neural network. So to recall, we're working with a vanilla transformer encoder, as we see here to the right. So we have this graph, we take the node features, and besides the node features, all the structural, all the directional information is encoded in those positional encodings. We apply some shallow neural network, add this to the inputs, and then just have an L layer and transformer and obtain our output embedding. And for this positional encoding, we basically follow some ideas from spectral attention by Kreutzer et al. On SciNet by Lim et al. And adapt this to our setting. So here we have the subset of the eigenvectors. We split up the real and imaginary part, stack those two. That's, I would argue, the same as we've done with the sinusoidal positional encodings all along. Then optionally, if you want, you can again look out for the sign ambiguity, right? We rotate it, we have some canonical rotation, and now there might be some eigenvectors for which the sign is not properly defined. So for those reasons, you can apply a sign net. We have this as a hyperparameter, and then we basically apply spectral attention. So we stack the eigenvalues. Then if you want, you can have like a transformer that here is not like between the nodes, it's between the different eigenvectors per node. So it's a very cheap operation because this is just like of complexity k squared times n. And then we do a reshape and some adaptation to kind of the internal dimension. So just like some MLP to make the dimensions to harmonize them. As I hinted in the beginning, or as I promised, we also have an alternative encoding, also a principled alternative encoding. I would argue, of course, you can also have like some other heuristics, like for example, like shortest path distances, which are subsumed by random walk encodings under appropriate assumptions. And for this, we extend the work by Li et al. Appeared at Europe's 2020 about those random walk encodings. What they had as an advantage, again, is they just looked into undirected graphs, so asymmetric. Therefore, in and out degree is the same, and also the forward and backward direction random walks are the very same thing. So they can just like ignore one of those directions. We include both directions, so we use A and the out degree to normalize it, A transpose and the in degree, and then do random walks in both directions. So we do a k-step random walk in both directions, and therefore then end up with a matrix like this. So we end up then with an n by n matrix times 2k with landing probabilities or random walk probabilities to reach those node pairs. And then following them, we apply some element-wise MLP. We aggregate back to node level that we get from this n squared representation to a node level representation, and do another neural network and then obtain those positional encodings. As an additional twist, because we want to keep k rather low, because that makes this whole approach quite expensive, we include additionally some random walk in forward and backward direction to have like some infinite step random walk to also have like those long range distances, and then we can choose like rather small k values. We have an ablation study in our appendix if you're interested in like what component contributed how much and which design decision, so check it out if you're interested in those kind of encodings. Okay, so those were the two positional encodings as promised. So now let's look at some experimental results. We mainly study 3 tasks. The first task is about distance prediction. Here the main gist is that a good positional encoding should then in the end also yield some awareness of distances and of relations in this graph, right? So we look at 4 different tasks. For example, one is reachability. So can I reach node V from node U, acknowledging the direction? Adjacency, which means predict the adjacency matrix itself. As we're looking in unweighted graphs like 1 and 2 are then classification tasks. So we have an F1 score to measure their performance. And we also look into 2 distance regression tasks for undirected distance and directed distance. So for the undirected distance, we just ignore the direction, then count the hops. For directed distance, we do the same just on the directed graph. Here we reported performance in RMSE. So for RMSE, lower is better, for F1, higher is better, and therefore we encode the performance also in colors. So this dark green means like it's a good performance, and this brighter color means it's not so good. For this, we sample Erdős-Renyi graphs. One, we sample directed acyclic graphs, and we also sample regular directed graphs. And then we study the generalization to larger graphs. So here I just like freely abbreviate this, like it's medium-sized graphs and large-sized graphs. So this is like a matrix of all the different combinations, and also having 3 different position encodings. So one, we use the graph Laplacian, magnetic Laplacian, and the random walk encodings. Here I should also say that we don't use like this vanilla definition I've been showing like the first half or like the most of the time in this presentation. Instead, we use this degree normalized version, which we find just like works slightly better. So the differences are not that big, but it works slightly better. So that's why we chose to use this normalization. But yeah, it just like the closed form solutions for this version are not that nice. That's why I omitted it most of the time. In the talk.
Do you really only add your positional encodings once to your features at the very beginning?
Yes. So here in those, we just add the position encodings in the very first layer, and then we apply 4 layers of transformer, and then do the output prediction. Of course, in this task, we also don't have any node features. So it's just like based on those positional encodings.
Okay. Good.
Then for the graph Laplacian, of course, this is we symmetrize the graph for this, and therefore by definition, this is not direction aware, and therefore this only works well on the undirected distance task. So here we get quite good results. For the magnetic Laplacian, we get the best out of both worlds. So we get good performance for the undirected tasks, but additionally we also are now direction aware, and therefore perform quite well on the other tasks, like for the prediction, for the classification, and for the regression tasks. For the random walk encodings, the picture is a little bit more fine-grained. So for the prediction of adjacency and reachability, we get quite good scores, which is also probably not too surprising. If you think about reachability, just means like there's a non-zero random walk probability, then those nodes are reachable. If I have like a long enough horizon in my random walk. And for adjacency, this is like basically for this k equals to 1 random walk. For single step random walk, is there a non-zero landing probability? For the distance, of course, this is a little bit more tricky. And another reason, which I will quickly go back, why this doesn't work that well for the undirected distance is also how we constructed the directed walk. So we just include the forward direction and the backward direction. And I assume if you want to also be good on undirected distances, then you should also include the undirected random walk encoding. We didn't do this really, but the main point is also that if you want to use random walk encodings, they can be super powerful. And they can do their job quite well. They're easy to handle with, but I assume that they might also require more engineering. So there's more like the guess of like, do you hit the right inductive bias for your application? Maybe you don't. Maybe it's hard to tell which distances are actually important. There are some questions in the chat.
Just about how, in the beginning, the question was, how do you represent the position of a node in a graph if you don't have a sequence? So, for example, the source may point to two different nodes. I guess that's the whole purpose of these positional encodings that you're developing.
Yep.
And then there was the point of use rope instead of sinusoidal, as in this paper. And there, yeah, maybe it would be interesting. Can you lose a few words of the relation of rope to sinusoidal positional encodings, the translation invariants, and do we have any rope analogs here?
I mean, as far as I understand the rope position encodings, those are also using like this complex sinoid or rotation matrices. And the main difference is instead of adding those, we're multiplying them to the input features, right? And by doing that, I guess like from what we can express, it should be pretty similar, but like they seem to work a little better than the sinusoidal position encodings. Did I miss any aspect of Rob? Did I oversimplify them?
I don't know how I was just very recently introduced to rope by Bowen, and so as far as I understood in rope, we don't like multiply our positional encodings in the beginning or something. Instead, we multiply our queries, keys, and vectors, or no, not even the vectors. I think just queries and the keys. There we rotate basically like two numbers in our feature vector, and we rotate it by a certain bit, and we rotate each position by just the same certain bit, and then we sort of if we then take our attention, or we do our matrix multiplication or query key multiplication, then we capture the angle between the rotations that we applied to our two number vectors. So to my understanding, this is quite different. And I don't think we have a same issue here, or like we don't need to think about this here, because we don't have any we don't need to solve this translation invariance issue here that usual sinusoidal positional encoding has, because here we don't have it in the first place, and we just use the graph Laplacian.
Are the rope encodings perfectly translation invariant? I guess I'm not too sure about it. Like from my perspective, it was basically multiplying this. You have different frequencies per dimension, so that's why you always have those pair of input features. But yeah, I guess it probably doesn't matter too much at this point, anyways.
Yeah. Anyway, doesn't matter so much. To understand the point of rope was to make it translation invariant, but here we have our clear graph, so to say. Yeah.
Okay. So then, I think I discussed this. The second task, which is a little bit more related to code, is about the correctness prediction of sorting networks. So sorting networks are a construct in theoretical computer science, being studied for several decades. And in short, a sorting network is just an in-place procedure for sorting a fixed length input with a fixed set of comparators. The details are not too critical here. Our task is then to predict the correctness of such a sorting network. So it's a graph classification task, and this correctness prediction is then related to satisfiability. And here we have this very nice correspondence between the sequence and the graph representation. So we have a sequence of operators which then always sort two inputs at a time. So here each horizontal line is one of the inputs, and at each comparator sorts those connected inputs, and in the end we hopefully obtain a correct sorting network, and then the task is to predict whether this was a whether this is correct, the sorting network. So it sorts all input sequences. So again, the main point is we have a sequence of some objects which are comparators, and we can directly also construct some dependency between those operators or comparators. So for example, the very first comparator here then corresponds to this very first node with the features 3, 4, which we encode with sinusoidal encodings, by the way, and then is connected to the 2 subsequent operators, and so on and so forth. So we have this sequence correspondence, and we have this dependency graph correspondence. And here it's very nice that like the sequence and graph representation is like perfectly aligned, so there are no tokenizer differences, and so on and so forth, as we would have them in many other applications. And that's also one of the reasons we chose this. And there's also a very nice way of thinking about like what does a sequentialization actually correspond to in such a directed graph. At least for this DAG, we can directly construct sequences, semantically equivalent sequences, just by topologically sorting this or ordering this directed graph, and each of the topological orders then corresponds to one valid sorting network that's semantically equivalent here. And we then train on a data set of those sorting networks, and the task again is to generalize to longer sequence lengths. So we train on sequence length 7 to 11, we validate on sequence length 12, and then we look at the test generalization, which means like sequence length 13 to 16. We have sinusoidal position encodings here, we have the random walk encodings, the graph Laplacian, and the magnetic Laplacian. So for the sinusoidal position encodings, we see that they actually work okay for the shorter sequences, so that we get quite some decent performance, but they don't really generalize well to those larger graphs. I can just imagine that the number of topological sorts, so all the possible sequences, is a quite large space, and that they have to deal with that. For the graph Laplacian, it doesn't really work well. It cannot distinguish direction, and distinguishing direction is actually critical in this application for good performance. Therefore, they also don't really work that well. And for the random walk and magnetic Laplacian, we see that they perform quite similar. Maybe the random walk encodings even have like some edge over the Laplacian encodings in this task, which means that probably the random walks are very well aligned with the distances that are necessary to be good in this task. In our main task, which is about function name prediction on the Open Graph Benchmark Code2 dataset, we look into source code. So there we have 450,000 Python functions, and given the function body, the task is to predict what is the function name of this function. For this, we first have the view on the data construction. So the Open Graph Benchmark basically takes an AST graph and then connects the nodes sequentially. So it's basically a sequence representation with a hierarchy on top. That's what the Open Graph Benchmark studies. And we also construct this data-flow-centric representation, which we see here in the table. We compare to the state of the art and to a vanilla transformer. So here easily denoted by GNN, with GNN and without GNN. So without GNN, we just have like a vanilla transformer. And with GNN, we basically have a GNN also transforming query and keys. So this is also known as like structure-aware transformer, and was the prior state of the art on this data set. And we then, of course, apply our random walk encodings and our magnetic Laplacian positional encodings to obtain some gains. We first started with tuning a little bit the pipeline. So there are some just engineering improvements we have over here. So therefore, we also already improved quite substantially over state of the art. Then we plug in our graph construction with the AST depth position encodings, which just means like how far is the node away from the root node of the AST, and obtain another gain. And then with the random walk encodings and magnetic Laplacian encodings, we even push the performance further, in total outperforming the prior state of the art relatively by 15% here.
So how notable do you find it that the improvements of adding this positional encoding or using your positional encoding or using your method compared to just using better engineering is quite small. What are these?
I guess, yeah, it's important that your setup is right. If your setup is not right, then like that's critical for deep learning. I wanted to be transparent about like where like each gain comes from. So there is some gain, but of course it's probably like relatively 2.5%. So it should be significant. Yeah, like if you look at the standard deviation, so that the gains should be like significant from a statistical standpoint. But yeah, of course,
I'm not
having the setup right is probably more important.
No improvement or something like that, right? It's clearly, you can look at the standard deviations, we see there's improvement, and it's just, yeah, it's like the depressing reality of our field that oftentimes some cool ideas or some sensible approaches don't help so much as like just getting the basics right and putting in some engineering effort. But I'm not sure.
I guess it's super important to first like get the basics right, especially if you have a new method. It might be even like challenging to get the basics right for reasons, right? So it's super important to focus on having that, and yeah, can make your method like look good or not that good, I guess.
Alrighties.
All right. So this brings me to the end of the talk. To wrap up, I hope I could convince you that directed graphs are important to model certain input modalities, and especially can have some benefits over other representations. For example, like sequence representations, if you recall the example in the beginning with the F1 score of how many different possibilities there are to write this rather simple function. So we should think about like getting graph structures exploited in different domains, and I guess there are like many opportunities left where this can really help. And yeah, what we added to the state of the art in this work is that we propose two position encodings. One is based on the magnetic Laplacian, based on spectral graph theory, and the other is using directional random walks. And if you use those, then even though we just use a vanilla transformer, we already obtain substantial direction and structure awareness in our transformer. So thank you for your attention, and yeah, I'm happy about any questions and discussion and so on.
Yes, thank you for the nice presentation and this walkthrough and explaining also some side things. And Dobrik is asking about CLRS 30. So do you know this data set, and have you also done any experiments?
I looked briefly into CLRS. I just like obtained some preliminary examples. I think you can make transformers work in that setup, but probably you will need to increase the training size a little bit, because there's like it's rather data efficient, the setup there. And yeah, the generalization like from training instance 16s to 16.4 is also like a very large gap you're looking at. So I guess like if you have sufficient data, that should work. But I didn't really like bring it to state of the art results, because I think like it's a little bit bisecting or a little bit beyond the scope of this benchmark to have like a lot of data. But I guess it would make sense to complement maybe some GNN approaches there, what I haven't tried really yet. What I also didn't talk about in the talk is that we also have like one small example or one small experiment on the sorting network task, where we also apply those positional encodings to GNNs and also see that there can be some gains. So I guess why not? This could be certainly tried out. It might help. Yeah.
Okay, and I think for the next one, it would be good to go back to the slide where you visualize your eigenvectors a little bit on this graph. And this is about intuition behind the phase and magnitude in the eigenvectors. So, for example, is there an analogy with the graph Laplacian spatial frequency modes?
Oh, now I have the right view. I will go back to this slide.
Yeah, that's what I meant. Maybe that's useful. Not sure. The question is about intuition between the phase, behind the
Yeah.
phase, magnitude of eigenvectors, and yeah, if there's an analogy to the graph Laplacian spatial frequency modes.
I mean, for simple graphs where you don't have like any cycles, it's not like not exactly precise the statement, but I think no, it doesn't really work. Like for sequences and trees, as we see here, the phase is basically encoding the directionality, and the magnitude of those eigenvectors is representing like this graph structure. I think that's how we can think about it, right? That's why we have this correspondence between the graph Laplacian and this magnetic Laplacian, which means that we are encoding the position with those imaginary numbers.
Yeah, but for me it's also. Do you want to say more about this?
Like I can answer to the second question, or we can stay with like the first point.
Then let's first move on.
But like for cycles, it's a little bit more tricky. I guess like the proper explanation is that in the end we're talking about like that the eigenvectors are minimizing the Rayleigh coefficient, right? Or that's kind of like the what they yield, like optimal solutions for this Rayleigh coefficient. And you can construct a very similar form than this quadratic form as we have it for the graph Laplacian. So it is about some minimizing some differences between like the eigenvectors between the neighboring nodes. And yeah, I don't know. There's also like an analogy like angular synchronization. I don't know if you talk about like in engineering applications where like similar problems come up. So there is some also like some literature on explaining like how this works out. In a very simple way, we can think about basically each edge introducing some phase shift in this eigenvector. So that's like how we see it for the sequence. Of course, for more complicated graph topologies, there might be some trade-offs you have to do. So for like if you increment if you rotate each eigenvectors a little further, then you would have an issue with this backward connection over here, because then the rotation would be very different, and therefore we have some trade-offs in more complicated graph topologies. But it's about like about that basically. And yeah, we have the eigenvalues, and the eigenvalues for appropriate choices of Q should still correspond to some frequency. So they should be like very similar from what they describe.
Then Marianne also asks, could you clarify how different frequencies are combined to produce a positional encoding? And is it just that each frequency then here in the end, when you add it to your vector, will correspond to a different channel?
Exactly. So if you look at the architecture over here, so then we stack real and imaginary part, and then we have like batch size times number of nodes times this k, what we've chosen, times 2. So here we first apply something on the level of each eigenvector, so for each eigenvector independently, and then in the end, after this reshape, we just like use an MLP.
I guess
we use an MLP to combine the different channels.
We can kind of ignore the D for now, and yeah, just pretend we only have our K, and we can ignore the ×2 that we do our stacking, and pretend we just have our K, and then yeah, this is our number of channels. Yeah. Okay. Then I was also confused a little bit about these cycles though. If we have a cycle, right, then your positional encoding, it's still arbitrary, right? Or there's some symmetry that we cannot capture. Yeah, and
what's your question? Sorry.
but this arbitrary positional encoding, it still captures the distance, right? The relative position in this graph. Now, if the analog of rope here, so to say, would be if we get rid of this arbitrariness and have, so to say, a shift invariant positional encoding, where we where we still have a notion of the distance as we would have if we did like message passing, where we look at the distances between each node or something like that, or the relative position or something like that. But we still have that, but we also have that with rotation invariance, if you want to call it that. Now, of course, it's not real rotation invariance, but yeah, I guess we know what's meant.
Yeah, I guess like if you view it from that perspective, that's a very valid point. There is like this ambiguity of eigenvalues, right? Like we have no sync nodes, for example, we have a circle, and we have repeated eigenvalues. Then we can look into like invariant quantities like that over here. Which I should have plotted this like for a single eigenvector. That could correspond actually like to like rope encodings in some way if you do this.
Really?
Like like you have this multiplicative thing, right? This product. It's not exactly the same, certainly, but you could approach it in a very similar way than those rope encodings, I guess.
Okay.
But yeah, there's some details, obviously, like they won't match up one to one. So there's still some thinking, but I'm pretty sure you could do some multiplicative thing that would resolve that.
In my very vague intuition, here resorting to this, what should we call it? The design and basis net solution would be to sort of incorporate all the symmetries, but by no longer distinguishing everything. And I'm not sure if that is true at all, or we would need Derek here to answer there. And we no longer have the full positional awareness, so to say. But I don't know, and I don't want to say too many wrong things here. I do that enough.
But yeah, like one last comment. Like if you look into the sign and basis invariant network, then at least like for the basis part, they basically operate on those kind of products, right? So this will yield an n by n product, which then describes like some relative like distances in some way, and then you would operate on those. And for those, if you have, since you have like this like actually this should be an inverse, therefore this C cancels out. That's kind of the thing why this works. And that's similar to what's being done there, I guess. Does this make sense?
Oh, well, still very vague, but I'm happy with it. Good. Then let's go for this one more question before we call it a day. What about the expressive power of the encoding in terms of directed graph isomorphism? That is nice. That is nice. The encoding understands the adjacency and reachability. I don't know. Any thoughts about directed graph isomorphism?
So we don't have any theoretical or also any empirical things into that direction in the paper. And I guess you will have similar challenges than if you look into like the traditional graph Laplacian. So I think in the spaces like sign and basis net, they argue that you need like those higher order IGN networks for like universal approximation. And I guess like similar things should basically extend to this here. So if you want to be like universal approximator and permutation equivariant in the same time, then you probably need like some constructs, maybe similar to those. There are probably also other possibilities. So the eigenvectors per se, I would say, if you, especially like if you take the full spectrum, are lossless. If you take like a subset of the spectrum, of course, it's a lossy compression. And with the full spectrum, you can reconstruct the adjacency or the Laplacian, which is basically the same in the end, information-wise. You can construct them from the eigenvectors. So there should be everything should be there. There are certainly some things you need to consider in practice.
Okay, now we all know a little bit more about magnetic Laplacian, scalar reminders about that, and with those we also now know how to do our positional encodings for directed graphs, and then how to do transformers for directed graphs. And if you want to hear more interesting stuff like that in the future, join us again on some Monday. And yeah, friends of the sun, see you next week. I hope you enjoyed as much as I did.